Hello everyone, welcome back to Simscope. In today's video, we are going to learn one of the most important concepts in digital signal processing and digital control systems, the zero order hold and first order holds as reconstructors. These blocks are widely used in PLC, digital controllers, servo systems, and digital to analog converters. Although they look simple in Simulink, they perform a very important task, reconstructing a continuous signal from sample data. In this tutorial or in this video, I have prepared 3 Simulink models. We will go through each model step by step, understand how it works, analyze the scope output, and then compare the performance of zero order hold and first order holds. So let's begin. Firstly, the model number 1 is a zero order hold. This is our first Simulink model. Let me first explain the overall structure. We start with the sine wave block. This block generates the continuous sine wave, and you can think of it as an original analog signal before any digital processing takes place. Our amplitude is 1 and the frequency is 1 radian per second. This is the signal we want to reconstruct. Now, notice that the output of the sine wave is split into 2 different paths. The first path goes directly to bus creator. This is simply the original sine wave. We are sending it directly to the scope, so we can compare it with the reconstructed signal. The second path passes through zero order hold block. Now this is the block we are interested in. Let's open it first. And you can see that the sample time is set to 0.5 second. But this means the block samples the sine wave every half second. But here's the important part. After taking one sample, it doesn't continuously follow the sine wave. Instead, it simply keeps that sampled value constant until the next sample arrives. That's why it is called hold block, and it literally holds the value. Next, we have bus creator. This purpose is simply to combine a multiple signal into one output. In our case, it combines the original sine wave and zero order hold output, so both can be displayed together on a one single scope. Let's run the simulation. Here we have 2 signals. The yellow waveform is the original sine wave. The blue waveform is the zero order hold output. Notice that the blue signal looks like a staircase. Why? Because the zero order hold only updates its output every 0.5 seconds. Between 2 samples, it ignores everything happening to the sine wave, and it simply keeps the previous value constant. Then, when the next sample arrives, it instantly jumps to the new value, and this process repeats in the entire simulation. That's why the reconstructed signal appears as a staircase. Right? Okay, let's focus on this section here. The sine wave is continuously increasing. However, the zero hold doesn't move, and it stays completely flat, right? Only when the next sampling instant arrives, it does jump upward. Again, it remains constant until the following sample. Again, this is exactly how most digital to analog converter works. Notice something else here. Near the peak of the sine wave, this is the peak of sine wave, and the output remains constant even though the original signal has already started decreasing, right? The yellow has already started decreasing, but the output remains constant here. This happens because the block is still holding the previous sampled value, and it won't update until the next sampling instant happens. So to summarize the model 1, the zero order hold samples the signal at fixed interval and hold each sample value constant until the next sample arrives. This results in a staircase approximation of the original signal. It simply says, okay, at time 0 your value is 0 and it hold the value until 0.5 hits. At the this is our first sampling period, and therefore it increased directly to jump directly to 0.47. Then it again hold the value at 0.47 until next sampling time happens at 1 second, and it jump instantly when it hits 1 second. Then it jumps to the next sampling value, and that repeats. Okay, now let's move on to the next model. Model number 2 is a first order hold. At first glance, it looks almost identical, right? The sine wave is still producing the original analog signal. One branch goes directly to scope, the other branch passes through first order hold block instead of zero order hold. Now the initial output is 0.5, and what makes the first order hold different? It does not simply hold one value constant. Instead, it takes two consecutive samples and connect them with a straight line. This process is known as a linear interpolation. And why do we call it as a first order hold? Because this linear interpolation is done or have is done with first order equation. Now I have already run the simulation. You can see that again the value, the yellow waveform is original sine wave, the blue waveform is reconstructed signal. Instead of a staircase, the reconstructed signal is much smoother, and if we zoom in, now you can see that one sampling time, which one is more prominent? Okay, first sample and the second sample. Between two samples, this output is gradually changing rather than keeping it constant here. It is gradually increasing, and the first order hold assumes that the signal change linearly between the two sample value. First sample here, second sample here, we're just drawing the straight line. That's why we obtain this straight line segment. Again, one sample here, another sample here, straight line. One sample here, another sample here, straight line. However, near the peaks, you may notice a small difference between the blue and yellow signal. This is because the sine wave is curved. Sine wave is curved here, whereas the first order is assume it is a straight line, even though it isn't perfect. The approximation is slightly better than the staircase produced by the zero order hold, right? So the key idea of a model 2, the first order hold, reconstruct the signal by connecting adjacent samples using a straight line and resulting into a smoother output. Next, model number 3. Now let's look at the complete reconstruction process. This model demonstrates what actually happens inside many digital control systems. Everything starts with a clock block, decimation of 5. Then the clock simply outputs the simulation time. As time increases, the output increases continuously, forming a smooth analog ramp. Then the clock output is connected to the idealized ADC quantizer. ADC stands for analog to digital converter. Analog to digital converter, right? And its job is to convert the continuous analog signal into digital value. In this example, the converter uses 4 bits. A 4-bit ADC can represent 16 different levels from 0 to 15. So our minimum value is 0 and maximum is 15. The ADC cannot represent every possible analog value. Instead, it rounds the input to the nearest available digital level. And this process is called as quantization. After ADC, we are giving to zero order hold and first order hold, and all the signals or all the outputs are displayed by the scope 3. Now you can see the waveforms. Firstly, the graph 1 shows the original clock signal. Notice that it increases smoothly, and this is our analog signal. Graph 2 or the second graph shows the ADC output. The smooth ramp has now become a staircase. This staircase represents digital value produced by the analog to digital converter. Now graph 3, the third graph shows the output of a zero order hold. Notice that every digital level is held constant until the next update. Constant, next update, constant, next update. The output changes suddenly from one level to another level, creating a familiar staircase waveform. And the final graph shows the output of a first order hold. Instead of remaining flat, the transitions are much smoother, and because the first order hold performs linear interpolation. So you can see that much smoother, though there is a but compared to this, it's more smoother, right? So final comparison between these two methods, the zero order holds simply keeps the sampled value is constant. This produces staircase waveform. It is simple, fast, and widely used in industrial systems. The first order hold connects the two adjacent samples using a straight line. It provides smoother approximation of a original signal and making it more suitable for applications requiring smooth motion or precise signal reconstruction. So today we have built 3 Simulink model. We learned how the zero order hold reconstruct signal using constant value. Second model, we saw how first order holds improves the reconstruction by connecting samples with a straight line. And finally, in the third model, we explored the complete process, uh, starting from analog signal, converting it into the digital form using a ADC, and then reconstructing it using both models. I hope this video helped you understand not only how this Simulink blocks works, but also why they are important in the digital control system. If you have enjoyed this video, do not forget to like, subscribe, and turn on the notification for more MATLAB and Simulink tutorials. If you have any question or suggestion for future videos, leave them in the comment below. I would love to hear from you. Thank you for watching, and I will see you in the next video. Thank you.